So this is one of a series of videos going to be looking at simulating 3 and 2D devices in OghmaNano. And in this video we're going to be looking at the silicon material system rather than any disordered material systems. So if you click on the new simulation button, you'll get this window which showing all different types of simulations you can do. And if you look at SI demos, so silicon demos, you'll see 3 demos. We've got amorphous silicon solar cell, an nMOS capacitor and a polycrystalline silicon. Today we're going to be looking at the nMOS capacitor, and if you double click on that you'll get this window up here. This device is effectively a capacitor, so it's got 4 layers, 1, 2, 3, 4 layers, and these top and bottom layers are effectively metallic contacts, so it's just like a layer of metal. And in between we have an insulator and a semiconductor. So there's a silicon dioxide and there's a silicon. And the way it works is just like a capacitor. So effectively you've got your contacts, you've got a semiconductor, and you've got your insulator. And charge will build up when you apply voltage to the contacts. Charge will build up along this layer here, and it will just act as a capacitor. So let's look at this in the layer editor. So if we look at it in the layer editor, we've got the insulator, which is that bit. We've got the silicon dioxide layer. And we've got the contacts. So if we just run the simulation, and we'll just go back through what this means in a second. So what this is telling us, this is the sort of the solver output. So without sort of going into too much detail, is all sort of initializing. And then what we've asked it to do is we've asked it in the JV editor, we've asked it to ramp between, so starting at 0 volts, we're going to start at minus 15 volts and we're going to go to 0.3 volts. So what the solver does is it starts off and it slowly tries to get itself to the start point, which is minus 15 volts, and then the simulation starts and we start sweeping the gate voltage whilst holding the body to 0 volts, and we change the gate voltage, increasing the gate voltage all the way up to 0.26 volts, and it finishes. So which is the gate and which is the body? Well, this is the gate and this is the body. It's just defined like that, and it says so in the contact header, so gate and body. So let's look at the results. So let's look in the snapshots folder. Oh, well, let's look at the JV curve. I mean, the JV curve, just before I open this file, I'll try and guess what it might be for a steady state simulation. If you just look at the layer structure, we've got silicon dioxide, so we've got insulator, so it's not going to conduct very much, is it? So the JV curve is basically going to be 0. So open up the JV curve, and it's got effectively some noise. It's just 0. There's nothing there because there's no conduction there. Yeah, let's look at results. So if we look in the snapshots folder, we can effectively choose what parameter we're going to look at. So let's look at phi, which is the potential. So what we're doing is on one side, so on the top of it, I'll just make this a bit bigger. So on top of it, we're applying, put this over here. So we're applying effectively our voltages to this top contact here, and we effectively, so that's why it's minus 14. And as we step forward through a simulation, this voltage here increases, and at some point it flips and it goes positive. So let's look what this does to the electron carrier density, Qn3. So what we've effectively got is got a very negative voltage here, and this is pushing away the electrons. So this is the silicon dioxide layer here, this is the silicon layer, it's pushing away the electrons there. So as we increase that voltage on this contact here, we're going to slowly start sucking electrons towards it, and there we go, we start sucking electrons towards it, and we start to get towards, not yet, but we start to get towards inversion in the channel. And we can look at the population of holes at the same time. So if we go Q, P3, we can look at effectively how electron and hole populations vary as a function of position. So that's effectively that, and you can play with any parameter you want here to your heart's content. So it doesn't really make sense to look at the conduction band. Well, I guess it does. So this is what it thinks the conduction band will be doing. We can look at the Fermi level, so electron Fermi level. Let's look at that. So this is what it thinks that the Fermi level is going to be doing in the device. And that's it really. So this is sort of a simple demo of a Is it worth? Yes. So let's just go back to phi, actually. And what we can actually do is we can plot that on the device in 3D. So this is actually what, by clicking that button there, what this actually is this is a plot of phi. Oops, can we zoom in? Would it allow us? Yeah, there we go. So this is actually a plot of how phi is changing in 3D, so you can sort of visualize the change. And the same with the charge density, you can also visualize what's happening with the charge density. Just zoom in 3D in the device. There we go, you get some sort of change at very high voltages. So, I mean, this is meant to be sort of a little fun demo to play with nMOS capacitors. If you want to change the electrical properties, you just look in the electrical parameter editor. So here we have, you can see we've set this one here to an insulator, and this is where we have our drift diffusion parameters here that you can play with. This button here enables drift diffusion equations, so you can see in the insulator we don't have drift diffusion enabled, but in the silicon we do. So that's really it. It's just a little fun demo, so I hope you enjoyed that demo, and thanks very much for watching.